In the last class, we discussed this configuration, which was nothing but a BJT inverter, or what is called as common emitter amplifier. Configuration. Common emitter amplifier configuration, this was called. So, we said input terminals correspond to base emitter, output correspond to collector emitter, emitter being common, it is called common emitter amplifier. And now, the relationship between the output voltage and input voltage can be derived, that is called transfer function. Okay. To derive the transfer function of this, V naught as a function of V I. So, we got this equation V C is going to be same as our V naught collector voltage V C E actually is going to be same as V naught, which is nothing but V C C if I C is the current in this minus the drop in this I C R C. So, that I C, these are different conventions adapted. This is capital I and suffix also in capital letters, it is called DC, okay, DC voltage, capital letters and suffix also capital, that is a convention for DC. Capital letters with suffix being small letters, it is RMS value of the AC, right, sine wave. Small letters with suffix indicate instantaneous values. At any given time, it may be indicating the instantaneous value of the voltage or current depending upon the letter that is used, I or V. Okay. So, we are now considering the instantaneous value of these, okay, voltages with respect to instantaneous value of the currents. No, V naught therefore is equal to, at any instant of time, is equal to V C C minus I C R C, that is always valid. So, we know that I C is equal to alpha times I E. We are ignoring the I C naught. So, I C is equal to alpha times I E at every instant of time, this is valid as long as transistor base emitter junction is forward biased and collector base junction is reverse biased, this transistor action takes place. And other relationship is between I E and V B E. We know that is equal to I E naught reverse saturation current exponent, okay, V B E by V T. V T is the thermal voltage, which is nothing but K T over Q, which is about 26 millivolts at room temperature. This relationship we have already derived in the earlier situation, and I E is equal to I E naught exponent V B by V T, which is named as I E naught exponent V I in this case, because V B E is the same as V I at every instant of time. So, now substituting all these things together, we get V naught equals V C C, a constant voltage, minus I C times R C. I C is equal to alpha I E times R C, which is equal to V C C minus alpha I E is equal to I E naught R C exponent V I by V t. This is where we had sort of stopped. This is the nonlinear relationship between input voltage at any instant of time and output voltage at that particular instant of time. So, this is all the time valid. And we said a plot of this if you plot, initially there will be almost VCC, and thereafter at about Vi equal to 0.5 to 0.7, this effect of current increase rapidly will occur, and then it will go to saturation. In fact, it is not going to come to 0, it will slowly come to 0. That is, this point is going to occur between about 0.5 to 0.6. Okay. So, this is let us say 0.6 volts. So, this is the nature of variation of output voltage with respect to input. We just said this is the region, this region is the region where the amplifier goes to saturation, here it is cut off, and this is the active region. So, this region is of interest to us, where delta V naught by delta V I, in this case nothing but the slope. For a change in input voltage, what is the change in output voltage, which is called gain, voltage gain. This is called voltage gain for the amplifier. Had this been linear, this would be constant, whereas here it is non-linear. So, this will change depending upon the operating point. Right? If I operate at this point, it will have some value. If I operate at this point, it will have some other value. So, delta V naught by delta V I, this is a small signal voltage gain. This is called small signal. Now, because it is non-linear, okay, this is valid. This is linear assumption is valid only for a small change in voltage. So, this slope is negative. What it means is, when the, what is negative slope indicating? When the input voltage is increasing, output voltage is decreasing. When input voltage is increasing, V naught will be decreasing. This is indicated by this. Vi increasing means this arrow, right? Output voltage is decreasing. That is why there is an inversion. So, this means that is why this is an inverter. Okay. When the Vi is increasing, output voltage is decreasing. That is what is meant by inversion. Okay. So, now again, if the input voltage is high, if the input voltage is high, output is low. So, if the input is high, output is low. If the input voltage is low, somewhere here, output is high. This is a very interesting thing. If input voltage and output voltage are both, if I denote high as 1 and low as 0, this is called the binary bit level, 1 and 0, high and low, positive logic, right. Then Vi, if it is 1, V naught is 0. If Vi is 0, V naught is 1. Or if Vi is A, V naught is A bar. This is the logical operation. So, this is also called a digital inverter as long as you are operating in the cutoff and saturation region. The V naught and V I should be such that the operation should be in the cutoff and saturation, not in the active region. So, operation is in the cutoff or saturation region, then it is called a digital inverter. So, if the input is high, output is low. If the input is low, output is high. If V I is 1, V naught is 0, and V I is 0, V naught is 1. This is an important basic building block of digital systems. Without this, no digital system can be fully designed. Okay? That means what we have learnt with diodes, the diode gate, we discussed AND gate and OR gate. By using just diodes, we can build AND gate and OR gate. This is the logic. We had seen this when we discussed applications of diode. Now, adding this operation is called A is input, A bar is the output. This is a NOT operation. NOT operation. So, with this NOT operation added, okay, we can have AND gate cascaded to NOT operation forming NAND gate, OR gate cascaded to NOT operation giving NOR gate. NAND and NOR gates by themselves can give you design of any digital system. Okay. Just using only NAND gates and NOR gates, you can build any logic system that you desire. So, if we incorporate this inverter as one of the basic building blocks along with the other gates that we have discussed, we can build any digital system, logic system that we desire. And if we operate in this region, if the bias is such that the operating point is in this region, which is the active region, it is then used for inverting. It is also an inverter, but inverting amplifier. This is called inverting amplifier. The gain is negative, or the slope here delta V naught by delta V I is negative. That is what is meant by inversion. Okay. If the voltage is incremented, output will be decremented. Okay. So, this is what is meant by inverting amplifier. For amplification to really exist, delta V naught by delta V I should be greater than 1. Voltage amplification, for example, in this case. If it is a voltage amplifier, the voltage gain has to be greater than 1. Now, that is the borderline defining what? Where exactly we are entering. So, if you plot this characteristics and draw a line with slope equal to -1, okay, on the characteristic, that particular point where the slope is equal to -1, it is separating the active region from the cutoff and saturation. Okay. And that defines in digital system design, you can discuss this as noise margin for okay, digital 1 or digital 0. What is the noise margin? Because if the output lies anywhere in this region, we are not sure whether it is a 1 or a 0. Only when it is in this region or this region, we are clear that it is either a 1 or a 0. So, this transition region is very important in digital inverters. The ideal inverter, let us now compare it with ideal inverter, will have a characteristic like, if this is VCC at exactly, let us say VCC by 2, it will not take place at 0.6, it will have equal noise margin for both 1 and 0. Okay. So, at exactly VCC by 2, this transition should take place and it should be abrupt. So, this transition should not take place at 0.6, it should take place somewhere much beyond this point, and it should be this is an ideal inverter. This should occur at VCC by 2, and the slope should be infinity, that means gain should be infinity. So, ideal inverter has characteristics like this. This is nowhere near ideal. The transistor inverter is nowhere near ideal. The transition is taking place at about 0.6 or so, and that also is gradual. Okay. So, we have now discussed about prominent characteristics of this inverter in terms of transition from high to low, that should be strictly speaking as abrupt as possible, so as to give the maximum dynamic range for the noise margin, etc. And this slope here should be infinity for the ideal inverter. In practice, you can compare it with bipolar junction transistor inverter, where the transitions take place at 0.6. This can be shifted suitably by adding additional diodes in series with this. So, you can just put additional diodes and shift the transition to maybe even at a point equal to VCC by 2, but the transition's character remains similar to this, exactly like this. It is not abrupt. Now, if it is operated at a certain operating point for using it as an amplifier, then at that particular operating point, bias point or operating point or Q point, we have a voltage which is a DC voltage, over and above which we can superimpose our time varying signal. So, this has a constant voltage. This voltage we will call it as VIQ, which is nothing but VBE quiescent. So, if we do that, then we saw that this equation can be rewritten as VCC minus alpha IE naught exponent into exponent VIQ by VT into exponent delta VI by VT. So, VI is given as VIQ plus delta VI. We just say the varying signal is superimposed over a quiescent voltage of VIQ. Then we can put VI as VIQ plus delta VI here and split this as exponent VIQ by VT into exponent delta VI by VT into RC. So, this is equal to VCC minus alpha IE naught exponent VIQ by VT. What is this? This can be called as IE naught exponent VIQ by VT is same as IE naught exponent VBEQ by VT. This is nothing but IEQ, right. So, this is nothing but quiescent emitter current. This into RC into exponent delta VI by VT. So, this whole thing alpha times IE naught into exponent VIQ by VT is nothing but IEQ. So, VCC minus alpha IEQ into RC. This exponent delta VI by VT, we are now going to expand it as 1 plus delta VI by VT plus delta VI squared by VT squared, so on. So, this is the output voltage V naught, is now equal to VCC minus alpha IEQ RC. What is alpha IEQ? ICQ. Alpha times IEQ is nothing but ICQ, quiescent collector current. So, ICQ, okay, because alpha times IEQ is equal to ICQ into, okay. So, VCC minus alpha IEQ RC is ICQ RC, okay, plus, okay, ICQ RC by VT, I am taking it inside, into delta VI. This is minus now, I am taking everything inside the bracket, minus ICQ delta VI squared by VT squared by factorial 2, okay. Then delta VI cubed by VT cubed by factorial 3, which is 6, so on. So, now you can see here VCC minus ICQ RC, VCC minus ICQ RC, we can call it as V naught Q, quiescent output voltage. So, this whole thing, okay, is going to be represented as V naught Q, quiescent output voltage, minus ICQ RC divided by VT times delta VI. This is an important parameter. What is that? There is some constant. ICQ RC is voltage, VT is voltage. Okay. So, this is a constant. This is called the amplification factor or the gain, okay, into delta VI. This is going to be therefore V naught Q plus delta V naught. Okay. Because of applying delta VI, there is a delta V naught at the output. That delta V naught will correspond to minus ICQ RC by VT into delta VI. That is the linear term. Then the nonlinear term corresponds to ICQ into delta VI by this squared. Okay. So, those should remain very small. For that to happen, we have to have this particular thing, delta VI by VT should be much less than 1. This is the assumption for small signal. Okay. This is because that exponent delta VI by VT we have expanded as 1 plus delta VI by VT plus delta VI by VT squared by factorial 2, etc. So, delta VI by VT factor should be much less than 1. This is called small signal. In which case the nonlinearity can be neglected, and I can consider that for a delta V naught there is a delta VI, or delta V naught by delta VI is equal to, how much is that? Minus ICQ by VT into RC, okay, which is indicating there is a inversion, and the slope corresponds to ICQ by VT into RC. This factor ICQ by VT is characteristic of the transistor amplifier, and that I by V is called a transconductance of the amplifier. So, this ICQ by VT, which is characteristic of the amplifier, RC is the load that you are connecting, is nothing but GM or transconductance, of the bipolar transistor amplifier, which is GM. the definition for GM therefore is GM is nothing but delta IC divided by delta VBE. Delta IC by delta VBE, because delta I naught, IC is same as I naught, okay, delta I naught by delta VI it was. Okay. So, delta IC by delta VBE at the given operating point. So, please remember this is an important derivation which tells a lot about amplifier, that it is an amplifier only for small signal. And what is small signal? The change occurring at the input should be much less than Vt. What is Vt? About 26 millivolts, which means much less than 26 millivolts means it should be of the order of millivolts, less than millivolts. So, if that is the case, then we can say that it is linear and the value of the gain is minus GM into RC. And what is this GM? Transconductance. What is transconductance? It is nothing but delta IC, which is now delta I naught, divided by delta VB, which is delta VI here. Okay. Change in collector current for a change in base to emitter voltage, which is okay, nothing but ICQ by Vt. Okay. If you remember, this is exactly same as 1 over Vt divided by IEQ roughly. Vt by IEQ is called Re in the diode, small re, right. Diode small signal resistance is nothing but Re, which is delta V diode by delta I diode. So, GM of a transistor is same as almost nearly, okay, 1 over Re, or strictly speaking it is alpha over Re, slightly less than 1 over Re because of the factor alpha. So, GM of a transistor is alpha divided by Re, where Re is delta V diode by delta I diode. In this case delta VBE divided by delta IE. This is same as delta VBE divided by delta IE. So, since the input characteristic is between emitter current and emitter base voltage is that of a diode, okay, this Re is the diode resistance that is occurring in the emitter equivalent resistance, that is delta V diode by delta I diode, which is same as delta VBE by delta IE, okay, which is defined as Vt by IE. So, this is got as Vt divided by IEQ. So, here it is nothing but GM, which is alpha times IEQ divided by Vt, that means alpha time divided by Re minus. So, this is an important definition, minus GM into RC is the gain. Now, we will consider this transistor as a switch, control switch, which is an important function. We want a switch to be closed at our command. This is a switch. Given a command, I want to close this switch, and given another command, I want to open this switch. So, a switch is either an open circuit or a short circuit. This is a heater element, which is nothing but a resistive element, right? Heater. I want to heat this, okay. Then I want the power to be connected. So, VCC is the DC voltage which will get connected when this switch is closed and disconnected when the switch is open. So, this is how our soldering iron and all those things can function now, right. I want to heat the heater element by connecting the power, and I want to sort of, as soon as I reach the temperature, I want to disconnect the power, okay, and again I will connect it, again disconnect it. Now, I might control manner, connect it and disconnect it, so that the temperature rises up to a point and it keeps on remaining around that point. Okay. So, this is an on off controlling system like our fridge, right. Our fridge is nothing but an on off controller, where the moment we switch it on, the temperature is reached, okay, certain temperature is reached, and as soon as it falls below a certain point, okay, set point, again switch compressor is switched on, and again it will get cooled and it will go to that particular temperature at which we want it. Okay, again there will be power switched off, okay, like that. This will be normally remaining, okay, at a sort of constant temperature, okay, around a constant temperature, okay, so that it is off on, off on, off on. So, that is a controller is called an on off controller, okay, very simple controller. Therefore, it is never going to reach this set point temperature ever. It will always fluctuate around the set point by a certain set magnitude. Okay, this can be adjusted. Such controllers require a control switch. A transistor can be used as a switch. Let us see how. We have just now discussed that a transistor can be brought into active region. From active region, it can be brought into saturation. What is saturation? We will see this. Saturation we will now define as a point at which, okay, it is violating the transistor action, in the sense no longer IC is equal to alpha times IE. Okay. When does it happen? When base to collector junction starts getting forward biased. It should be, strictly speaking, reverse biased when we have transistor action. We do not want this switch, which is now the transistor acting as a switch, to remain in the active region. Okay. So, this is the difference between amplifier and a switch. This transistor should not remain in the active region, either it should be off. Switching it off is easy. I can simply make this 0. So, this is not forward biased. So, if Vi is 0, transistor T is off. This is the simplest way to switch it off. Right. So, IE is 0 when Vi is 0, and therefore, there is no IC. Okay. So, this is off. The switch S is open. The only current that will now flow in this whole circuit will be IC naught, strictly speaking, because the collector base junction is reverse biased to an extent equal to VCC, because there is no IC. Okay. This voltage is same as very nearly equal to VCC, and therefore, only the reverse bias saturation current flows, that is IC naught, which is very small. So, you can for all practical purposes ignore the current flowing in the circuit. Therefore, the switch S is off. Even in a practical switch, only when it is open, we can say that it is, okay, very high resistance. It is not strictly infinite resistance. Okay. Still there may be some leakage current flowing. Like that, our transistor also has certain amount of leakage current flowing, which means it is not an ideal switch. So, with Vi is equal to 0, T is off, or switch is off. And with Vi equal to, let us say, VCC. So, Vi equal to 0 may correspond to digital 0, okay, and Vi equal to VCC may correspond to digital 1. So, actual command signal comes from a digital inverter maybe. Okay. So, it is either high or low, there is no intermediate value it is going to take, and therefore, when Vi is equal to VCC, we want this switch to be on. Now, you will understand the reason for putting RB. If I do not have this RB at all, then this, when it goes to VCC, if it is not there at all, this VCC will come across base to emitter junction, and there will be enormous current, because even for 0.5 to 0.6 volts there will be very high current. So, it cannot sustain this much amount of forward voltage, and therefore, this junction will collapse, it will get destroyed, okay, because there is no current limiting. So, RB is the current limiting resistance put in the base. So, this is an important resistance to be put in the base of a switch, this you must remember, right, when the transistor is being used as a switch. This will be limiting the current. What is the current now? So, V I is equal to, when V I is equal to V C C, the current is going to be V C C minus V gamma, which is nothing but V B E divided by R B, that is the base current. When V I is equal to V C C minus V B E is of the order of 0.5 to 0.6. So, V gamma, okay, is nothing but V gamma. So, VCC minus VBE by RB is the current. So, you can fix the current at any satisfactory value. What is the current which you will select? When such a current flows through this transistor, the transistor should go to saturation. It should not remain in the active region. Let us assume that this resistance is RC. Right. So, if the transistor is going to saturation, then the current in the circuit both will have to be forward biased. Let us say this is 0.6, this is 0.6, that means this voltage is going to be 0 volts. This is forward bias, this is also forward bias, this will be 0 volts. Then the current in this is going to be VCC by RC. So, the maximum current that can flow through this is VCC by RC. So, IC max corresponds to VCC divided by RC. If the transistor at that point of time has gone to saturation, then the base current should be such that it is in saturation. What does it mean? That means the relationship, that is IC is equal to alpha times IE, is no longer valid, right. What it means is IC equal to alpha times IE is no longer valid. Okay. IC, here we know IB. What is IB? IB is equal to, we know that IC plus IB is equal to IE. This is always valid. This is IB, this is IC, and this is IE. IE is equal to IC plus IB by Kirchhoff's law, and this, if it is satisfied, IC is equal to alpha times IE. Okay. So, IE is equal to IC by alpha. I will replace IE because we want to find out the relationship between IC and IB, right. So, I will eliminate IE from this. IE is equal to IC by alpha. So, we have now IB equal to IC, okay, minus, in fact, IC by alpha minus IC from this, or IB equal to 1 minus alpha, okay, by alpha into IC. Is it clear? Or IC is equal to alpha by 1 minus alpha times IB. This factor is popularly called beta. So, beta is equal to always alpha by 1 minus alpha for the transistor, right. So, that into IB. If, for example, alpha equal to 0.99. Find beta. Beta is therefore equal to alpha by 1 minus alpha, which is 99. Right. Is it clear? So, please remember, if alpha is very close to 1, beta is going to be very high. Right. So, beta is the relationship between IC and IB, and if alpha is equal to 1, beta is going to be equal to infinity. That means, why is it infinity? For a finite collector current, we have 0 base current, right. So, alpha and beta are related by this, please remember this. So, in turn we can find out alpha as from this beta divided by 1 plus beta. So, prove okay, alpha is equal to beta by 1 plus beta. So, from this relationship you can prove that. Now, we have this particular relationship wherein we want IC equal to alpha IE not to be satisfied, because transistor has gone to saturation. When will it happen? If I make the base current such that it is more than what is going to be determined by this. That means, if IB is equal to IC by beta, this relationship is satisfied. Transistor action exists. If IB is equal to IC divided by beta, then transistor action takes place. If IB is greater or much greater than IC divided by beta, then the transistor is in saturation. That means, in this case the transistor is in active region, because transistor action still takes place. But if IB is much greater than IC by beta, transistor action does not take place. Why? That is because both junctions are getting forward biased. So, we are therefore using this information in order to force the transistor to saturation. If both the junctions are forward biased, then the whole transistor can be replaced by a single node, because this is a short circuit, this is a short circuit, the entire thing is almost nearly equivalent to a short circuit. That is what a switch should be, right. Why should it go to saturation? Why can't it be in the active region? That may be a question. Because then it is not going to act as a switch. Switch, when it is closed, has 0 voltage drop across it, and current can be anything, fixed by this resistance. So, in order to make it look like a switch and to make the current determined by this resistance, we have to make it go to saturation. Otherwise, current will always be determined by the input voltage. The input voltage should not determine the current. The current should be only determined by RC. So, this is an important design requirement. That means, IB should be much greater than VCC minus, that is IB, which is this, should be much greater than VCC divided by RC, that is the collector current, maximum collector current, divided by beta minimum. Now, what is this beta minimum? Beta is not a factor which is going to remain constant. It might change with respect to temperature, etc. Operating point and all. So, you have to take the worst case value for beta. This is given by the manufacturers. There is a minimum value that you can take for the beta. So, under the worst case also this should go to saturation, right. So, VCC by RC is the maximum current, that divided by beta minimum, okay, even that current, okay, drive is exceeded. Okay. So, the base current should be greater than that. If you make it too large compared to that, then it might damage the junction. So, that is why this is called a current limiting resistance. This cannot be made, RB cannot be made too small, RB cannot be made too large. The maximum value for RB is limited by this equation. Okay. Minimum value is limited by the maximum base current that you can permit through the transistor without damaging it. So, both maximum and minimum limits for the base resistances are determined by the fact that the maximum resistance is governed by this equation, minimum resistance is governed by the fact that base current cannot exceed a certain value without damaging it, right. So, any resistance within that range must be put here, okay, in order to design it as a switch. This may be therefore called a power switch. This transistor may be capable of sort of taking currents of the order of amperes, okay, and still act as a switch. This may be a relay coil, okay, which may take hundreds of milliamperes maybe to sustain some switching action, right. So, these are commonly used in control circuits for controlling relays, okay, heater coils, etc. So, design of a switch is very important, and you should make the transistor necessarily go to saturation. Okay. Now, this is unlike an amplifier design, where obviously I will not put any series resistance. A series resistance will cause unnecessary loss in signal. So, Vi is applied directly to the base. In the case of a transistor being used as a switch, only then I will put a current limiting resistance. Okay. If I am using the transistor as an amplifier, Rb has to be as small as possible necessarily. If okay, you will not put a series resistance, it will be 0, because otherwise you lose certain amount of signal in the series resistance. Only part of the signal will appear at the input, and therefore, when it is being used as an amplifier, Rb is 0. Okay. You will not put a resistance there. So, this is to be noted in the difference in design of an amplifier as against a switch. The switch normally gets as its input, again you have to note, either a high or a low. The low is always 0, because you do not want any voltage, okay, especially to pair. You can simply ground it. High is always necessarily the supply voltage. So, these are the two inputs which come into existence in discussing a switch and its performance. No other input need to be considered. Okay. Whereas, in the case of an amplifier, the input to be considered, okay, is at base directly, and it can be changing depending upon the operating point and the linearity you want, okay, and the dynamic range you want. So, we will revert back to discussion about amplifier with Vi being applied here, and this is not a heater element any longer. This may be the load resistance, Rc. So, Vi is at Viq plus delta Vi. Input is applied like that. How do you apply this? Okay. Viq can be a battery. Now, delta Vi should be a source which should come in series with it. So, that this is how do I do it? I have to put a battery which has a voltage of Viq in series with a small signal of delta Vi. in order to sustain this kind of thing. At that point of time I can get V naught, which is V naught Q plus delta V O, that is what we have said. Now, we will discuss how this can be done. Okay. One way to do it is put a battery in series with a source, but this source, okay, has to come in series with the battery. That means there is no common ground with respect to this point emitter. This has no common terminal. In our amplifier design and sources etc., we have been always talking of a reference common point, and if we take this as a reference point, all the voltages have to be sort of discussed with respect to this point. So, the AC voltage should be really applied with reference to this point. So, normally the sources are independently coming, okay. They are always giving you source voltage with respect to a common ground. If you want an arrangement like this, the only way we can have it is you have a common AC with common ground and then couple it by means of a transformer. Okay, you know about transformers. This transformer can couple this signal to this like this. Okay. So, either a transformer coupling has to be done, or how do we do this further? One way to do this is to introduce a resistance here, so that this is not biased by means of a voltage at all. So, if I add whatever some DC voltage here, let us say we have VCC and then we put RB here. Okay. This is now being biased by means of base current, no longer base voltage. Earlier I was putting a battery which was VIQ. Now, no longer a battery is put, okay, like that. I am having the same battery VCC, okay, and putting a series resistance there. I do not want to use another battery. I would like to use the same battery here. Okay. So, VCC in series with the resistance, if I put, just now while discussing switch, we know that a base current gets fixed here. What is the base current? VCC minus V gamma divided by RB. So, it is biased. This is called current biasing. The earlier one was voltage biasing, right. If I do this current biasing, where the current IBQ gets fixed as VCC minus V gamma by RB, then I can superimpose an AC by using capacitive coupling, right. This capacitor will block the DC and will couple the AC. So, this is the advantage of using current biasing instead of voltage biasing. So, instead of using a battery whose value is VBEQ, and what is the order of VBEQ? Of the order 0.5 to 0.6, I can use this current biasing. We will discuss further about this in the next class. Biasing a transistor.